Okay, so we are continuing our discussion of the stress-strain curve, and now we will move on to the concept of true stress and strain. So earlier we called our measures of stress and strain the engineering stress and strain, which suggested there should be perhaps another type of stress and another type of strain. So that's presently what we are discussing. So for this purpose, let's first define A to be the deformed area at any stage of loading. Okay, so the initial undeformed area was AI. So as the specimen deforms, as you pull on it, the specimen will probably get thinner, and the cross-section area will therefore decrease. And that cross-section area is now going to be called A. If the deformations are small, which is the case certainly if we are in the elastic region, then the difference between the initial area and A, it's negligible eventually. But if the deformations are sufficiently large, well into the plastic region, then the difference might be significant. And what I like to highlight at this stage is, in general, A is taken to be the smallest deformed area throughout the gauge portion of the specimen. Remember that at some point the specimen might show necking as we pull on the specimen. So this is the way the specimen looks after the necking occurs. This is the gauge portion of the specimen, not an excellent drawing, but here you have the neck formation. So when we're talking about A, it is the smallest area on the over the cross-sectional over the gauge portion of the specimen. If necking has occurred, then I have to look at the portion where necking has occurred, because that's where the area is smallest. Now, having said that, now we can easily define the first new quantity, which is the load divided not by the initial undeformed area, but actually by the deformed area, and we're going to call it sigma tilde to distinguish it from our engineering stress, and this quantity is going to be referred to as the true stress. Okay. So now we can easily manipulate this expression as follows. First, I can, instead of dividing directly through A, I can divide first through AI, and then I can multiply with AI over A and end up with the same definition. And subsequently, I can observe that the first quantity here is sigma, and the second quantity here is certainly something that is greater than 1, because when the specimen deforms, the cross-sectional area is going to become smaller. So AI is always larger than A. So what we see, therefore, is that the true stress is expected to be larger than the engineering stress. Okay. Now, this definition, the way we've defined the true stress, is valid all the way onto failure. And what I mean by that is that if you have the engineering stress strain curve and let's draw the ideal one, and at every point along this curve, obviously you know the value of sigma. If you also know the value of AI over A, so in other words, AI is already known. If I know the deformed area at any stage of loading, then I can find the true stress as follows, right? The true stress is sigma tilde, sigma AI over A. And I can use that relation to convert true engineering stress to true stress. And this relation between true and engineering stress is valid all the way up to failure. Now, then, of course, if there's a true stress, we can imagine that there's also going to be a true strain. Now, to introduce true strain, First of all, let's call it epsilon tilde, identically with the notation for the true stress. And let us first, before we define that, let us first, let's do it like this. Let us first recall the engineering strain. Now, the engineering strain, epsilon, is defined as follows. Now, I'm going to pick a definition that is somehow going to make the final that's going to match the expression that we already are familiar with, but I'm going to make it in a way that looks slightly different. Now, what we're going to do is we're going to take our specimen. It has an initial length of Li, right? And I'm going to extend it a little bit. Okay, so not all the way to the final deformation that I'd like to reach, but by a certain amount delta L1. So for instance, if I concentrate on the gauge portion, and let's say the gauge portion of the specimen initially looks like this. Now what I'd like to do eventually is I'd like to reach some level of deformation that perhaps looks like this. So the change in the length of the gauge portion is going to be delta L. But the way I'm going to reach delta L is by taking various steps. First, I'm going to extend it by a small amount, delta L1, and then by another amount, delta L2, by an additional amount, delta L3, etc. Each increment is going to be coming into my expression for engineering strain as an addition to the total strain. So for instance, right, the first strain that I had is a tiny increment, let's say that much, right, over the initial length. That's a small change in the strain. And then I change the strain a little bit more, and that change is the change in the length, which is going to be called delta L2, divided by the initial length. And I can keep doing this for additional incremental changes in the overall length, delta L3, etc., and until I reach the overall deformation, which is going to be called delta L. So when I look at that expression, the total strain is going to be sum over many small increments, let's call them alpha, delta alpha, divided by the initial length of the specimen. And of course, the top portion is nothing but delta L, so what I've obtained is delta L over Li, the change in the length of the specimen divided by the initial length. So that is, I'm closing the parentheses now, that is the definition of the engineering strain. So let's move the definition for true strain down below here. So now we're going to define the true strain as follows. Well, remember, the motivation for true stress is that we divide the load not by, at any stage, by the initial area, but instead by the actual deformed area. So that's the motivation behind calculating the true strain. So now I'm going to do the same experiment. I'm going to take the initial gauge and initial specimen of initial gauge length Li, and I'm going to try to extend it to an overall change in length delta L. And every time I'm going to make an incremental addition to the strain, but this time not to the as the engineering strain, but to the definition of true strain. And it's going to work as follows. First, I extend by an amount delta L1, and I'm going to divide it by the current length of the specimen. At the start, the current length, let's call it L1, that current length is certainly equal to the initial length of the specimen. Okay, so that is my first step in loading. Okay, so you see that the first step is the same for engineering strain and the true strain. Now, when I make the incremental addition to the overall true strain, the difference from the engineering one is going to be that I'm going to extend the specimen by delta L2, and I'm going to calculate the incremental change to the true strain as the change in the length, divided by the new length of the specimen. The new length of the specimen is defined to be the old length divided by the change in the previous length, okay? The change in the length in the previous step, okay? So In the engineering one, it's the change in the length divided by the initial length, change in the length divided by the initial length. In the true one, it's the change in the length divided by the first length, change in the length divided by the second length, and the second length is the first length plus the change in the first step. And this way I continue. So I add delta L3 not divided by Li, but rather by L3, where L3 is L2 plus delta L2, and etc. I continue in this manner. So now, although the expression here is sigma alpha, sum over all delta L alphas divided by Li, here the expression that I have is sum over alpha, delta L alpha divided by the current length L alpha. Okay, so now the expression is very similar, except that I'm dividing by the updated length. And in that sense, the motivation for true strain is the same as the motivation for true stress. I divide by the updated area and here by the updated length at each step of loading. And now that is the definition, a definition for true strain. However, there is a complication. The definition of true stress is independent of how many steps I take to a certain point in loading. At a certain point in loading, I have a cross-sectional area A. Doesn't matter whether I take 10 steps or 20 steps or 100 steps to reach that deformation. I eventually will obtain the deformation, that's the deformed area A. P over A is the true stress. Same thing for engineering strain. It doesn't matter how many steps I take to reach an overall length change of delta L. The definition of engineering strain is delta L over the initial length. Now here, however, I have a sum of delta L alpha over L alpha. Now it seems that the value of this quantity will certainly depend on the number of steps I take. In other words, if I want to extend to an overall deformation of delta L, I can do this in 10 steps, 20 steps, 30 steps, 100 steps. Now the question is, how many steps shall I take? And whenever you are in doubt, the question is in some sense similar to the definition of stress. Well, I'm going to define load over area. What should be the size of the area? The answer is that the size is infinitesimally small. So here the question is, I'm going to take steps. How many steps? How large should the steps be? And the answer is the steps should be infinitesimally small. And if you do that, essentially, you end up with the expression for true strain, which is the sum over many incremental steps divided by the current length of the specimen. And now because the steps are incrementally small, very small, infinitesimally small, the overall sum is replaced by an integral, and that integral goes from the initial length to the final length of the specimen. Okay, and therefore I can now calculate the simple integral, which is the natural logarithm of L over Li. In other words, the final length over the initial length of the specimen. Now, what you can notice is, first of all, these are definitions. I should note that we should know by heart. Okay, the true stress and the true strain. Now, what we can notice is that I can write the same expression as Li plus delta L over Li. So here we have the final length L, which is equal to ln1 plus delta L over Li, which is nothing but the engineering strain. And therefore, similar to the relation between engineering stress and true stress, we have a relation between the engineering strain and true strain. And that relation is that one is related to the other through that relation. It's not hard to derive if you don't exactly remember or memorize that relation. As soon as you know the definition for true strain, then you can easily go towards that one. Okay. Now it turns out that this relation is valid up to necking. Okay, and the reason is that what we are doing is we're monitoring the strain, either true strain or the engineering strain, through quantities that have to do with the length of the gauge portion, but the length of the gauge portion after a while becomes meaningless because all the deformation eventually localizes into a very small region that we called necking, and if you monitor the strain over the whole gauge portion, you are essentially doing a mistake. Most of the length changes will be occurring over a very small area that are in the vicinity of the neck region. So the cross-sectional area can be chosen right at the neck region, and therefore this is true up to failure. But because in these definitions so far I have used the length of the gauge portion, the relation that we have here, and for that matter the definition that we have for the true strain, is meaningful the way I've written, only up to necking. Okay, all right, so now what we have is the definition for true stress and strain. Now what you might wonder at this stage is, well, how do the two quantities, the two sets of quantities, compare with each other? And to see that, what we can do is we can plot on the same axes, set of axes, strain versus stress. And first we can draw our typical stress-strain curve. This is the engineering one. Now, if you carefully convert the engineering stress-strain curve information to the true stress-strain information, it turns out you get a curve that looks as follows. Now, first of all, the stress is going to be larger. We can easily see that because the load at any stage of loading is given. But for the engineering stress-strain curve, we divide the load by the undeformed area, whereas for the true stress curve, we divide the load by the deformed area, which is smaller, and therefore, as we said, the stress is larger. So stress is eventually the red curve. The true stress-strain curve is going to be larger. And here's where necking occurs, and eventually, if I carefully convert the engineering stress-strain information to true stress-strain beyond the necking region as well, I've mentioned some limitations. Again, I refer you to your book if you want to do that carefully. At this stage, we don't need to delve into more depth. What you will observe is the true stress-strain curve, the red line, which has two characteristics. One, it is above the engineering one. Two, extends further in terms of strain values as well. Okay, now there's another important feature that we do need to emphasize at this stage, and that feature has to do with the relations between true stress and engineering stress, as well as the true strain and the engineering strain. Notice that they have this similar quantity 1 plus epsilon appearing eventually inside. So I am sorry, I'm just going to delete that quantity because I haven't derived it for you yet, but let's easily convert that piece of information into what we already have derived, which is AI over A, which we defined to be, or observed to be, larger than 1. So first of all, what we are observing, and that's the way I have drawn that those two lines, what we know is that if the deformations are small, the initial and deformed areas are very, very close to each other, and also if you do a Taylor series expansion of ln1 plus epsilon, for small values of epsilon, you will see that this function delivers you approximately epsilon. So in other words, at very, very small values, at small deformations or small values of strain, sigma tilde is approximately equal to sigma and epsilon tilde is approximately equal to epsilon. They're not the same, but for all practical purposes, they are very, very close to each other. And that's what we observe here. Certainly in the elastic region, remember this is an idealized plot. This curve should be a lot steeper in the elastic region. In the elastic region, deformations are small, strain is very small, and therefore the two lines are very, very close to each other. When plasticity starts to become appreciable, then deformations are significant, the specimen starts to deform a lot, and eventually the two curves will significantly deviate from each other. But even into some portion of the stress-strain curve within the plastic zone, the two curves can be quite close to one another. So when deformations are small, the two curves are not easily distinguishable from each other. And we're going to make use of that information at various stages. Now, there's one final piece of information that we will make use of, and that has to do with an expression that I just wrote and then realized I haven't derived it yet. So let's have a look at what happens within the region where there are plastic deformations. Now, it turns out that when you do an experiment, you take a metal, and this is also true for polymers, but you take a piece of metal and you pull on it. Okay, of course, I'm exerting a certain amount of load. It's not sufficient, but certainly this thing will deform elastically. Now, when the specimen deforms elastically, let me ask you a question. Does the volume of the specimen, and when I talk about the specimen, I'm only concentrating on the gauge portion of the specimen. When I pull on the specimen, is the volume of the specimen, right? Length times this distance times that distance. Is that volume changing? Okay, I'm loading it. Deformations are elastic. The question is there a change in the volume of the specimen? Okay, so let me pause for a few seconds and you think about it. Well, I don't have to pause because you can, of course, you do that yourself. Well, now the answer is yes. Well, how much does it change? Well, we know that it changes through the volumetric strain. So it depends on the strains. The volumetric strain is a measure of volume change over the initial volume of the specimen, and that is defined to be the sum of the three strains that the specimen experiences, the three normal strains. So the volume does change. Okay, but now let me do the following. Well, I'm going to pull on the specimen a lot so that it deforms significantly, and perhaps it even fails, it breaks apart. And before I load the specimen, I measure the volume of the gauge portion, and after I break it apart, I measure the volume of the gauge portion, right? So before deformation, it's going to look like this. That's the volume. The volume is the initial length times the area of the gauge portion, and then I'm going to break it. There can be some necking. So I have two stages of thinning here. One has to do with the fact that I'm monitoring the gauge portion, which is thinner than the portion where I have grips, but also it has further reduction in cross-sectional area due to necking towards failure. So that is the gauge portion after failure. And what one can do experimentally is measure the volume of the gauge portion before and after failure. And what one observes is that the volume is almost the same. So notice that when I break the specimen, all the load is removed. There is no more, well, let's say significant, or idealize it, let's say, there is no more elastic deformation in the specimen. There is only plastic deformation remaining. So here it says significantly and purely plastically deformed broken specimen. Here it's the undeformed specimen, and I measure the volume here, measure the volume there. It turns out that the volume is almost the same. So I'm not talking about a negligibly small volume change. I'm really talking about a very, very, very small change in the volume such that we can virtually say the volume has not changed. Okay, so if there is any change, it's even smaller than the volume changes that one observes in the elastic portion of the curve. So it's really negligible. And therefore, one comes up with the conclusion that plastic deformations alone do not change the volume. Okay, and when I say change, again, this is an idealization, but a very, very good idealization. And therefore, if I look at the portion of the curve at some earlier stage before the specimen breaks, and I'm going to look at a region, I don't have to, but I'm going to look at a region before necking occurs. So the specimen is slightly longer now, it's slightly thinner, and the current length is times the current area is the current volume. So what we are saying here is that the initial volume, which is AILI, is for all practical purposes equal to the final volume, which is AL times V. And therefore, what we are observing is that the ratio, so I will divide both of these sides by A first, and then I will divide both sides by Li. AI over A is equal to L over Li. But L over Li, we've already done this before. The final length is the initial length plus the change in the length divided by the initial length again, which is equal to 1 plus epsilon. And so we have found out that the ratio of the initial to the final area is simply 1 over 1 plus epsilon. So what I can do, if you like, is I can find two alternative expressions for these. So first of all, I can write sigma tilde is equal to sigma 1 plus epsilon. Okay, so what I've done is I've replaced AI over A with that expression. Or alternatively, I can write epsilon tilde is equal to ln AI over A. Okay, now we have the alternative expression for the strain that we have already derived and used. Same one, and we have the alternative expression for stress that we have already derived and used. So now the difference between these two sets is the following. The set on the left and the set on the right, they are equivalent definitions all the way up to necking, but beyond necking, because 1 plus epsilon eventually is an expression that has to do with the change of length within the gauge portion, but beyond necking, remember that change in length of the gauge portion is meaningless because all the strain is being localized into the necking region. So that expression, the relation that relates that to AI over A to 1 plus epsilon is really a relation that is meaningless beyond the necking region, just like we argued earlier for that expression. And therefore, whenever we look at the left-hand side, the quantities that have to do with 1 plus epsilon, these will be limited up to necking, whereas the ones on the right are valid all the way up to failure. However, there is a practical difficulty. The practical difficulty is that if I want to convert true stress and strain to engineering stress and strain, the definitions on the left are easy to use because as soon as I know engineering stress and strain, I can immediately calculate the true stress and strain, whereas to use the definitions on the right, it's not sufficient to know what the strain is. It's also necessary to additionally measure the cross-sectional area during deformation. And if necking occurs, I have to measure the small area that is in the vicinity of the necking zone, which is very, very hard. So these relations are nice. They are valid all the way up to failure, but they are of not direct experimental applicability unless you have a good way to measure that cross-sectional area. Whereas on the left, what I have is a simple expression. You give me the engineering stress and strain, I immediately tell you what the engineering true stress is, and I immediately tell you what the true strain is, right? So the ones on the left are more practical, but beware of their limitations. Okay.